Okay, welcome back, and let us do today the Clausius inequalities or theorems. Okay, so if you remember from the previous video, I said that Carnot was probably one of the fathers of thermodynamics, and the reason is this one. So let us do just recall Carnot, cycles. What do we have? So the Carnot cycle, basically, if I do a simple figure, let's say TV is a cycle that operates between two temperature reservoirs this way, where here will be Q hot, and this is over here Q cold, and that basically equivalent to, let's say, our Carnot cycle operating between a hot reservoir and a cold reservoir, and this will provide work. So from the Carnot principle, it was said that the ideal Carnot cycle for power will be the one that will give you an efficiency of 1 was derived 1 minus T cold over T hot. So if you want, this cycle will be reversible. Okay? And the general expression was actually 1 minus QC over Q hot. So this is the general. Okay, so let's see where Clausius was really smart. So Clausius, what he did is he said, let us look at a general cycle. Compare PV or TV, doesn't matter, let's say T or PV. Because once you go to a general cycle, they're not going to look this way. They're probably going to look more like something this way. Okay? And imagine here you still have your hot reservoir. And you will still have over here your cold reservoir. So if you think about like when you do the integration of a function, what do? When you integrate something, basically what you do is that you break it into different rectangles. So over here, if the big one is a general cycle, what Clausius does is that he's going to break all this big one into an infinite number of, let's say, Carnot cycles over here. So you want this one here will be delta Q hot. So this will be here delta Q cold. Let's say I go to the next one. This could be delta Q prime cold. And on top here we could have delta Q prime hot. And you can keep doing the same thing, let's say up to here where you have delta Q double prime hot. And on this side, delta Q double prime cold. Okay? So basically you break a general cycle into an infinite number of small Carnot cycles. So let's see, what would happen for the first cycle? So for the first cycle, we know if this is a Carnot cycle, we can basically rewrite this expression over here, 1 minus, so let's say it will be T hot T cold. So we have 1 minus T cold over T hot equal to 1 minus delta Q prime cold, or let's remove the Q prime over here, over delta QH, so no Q prime. So now you see you can eliminate the 1, the negative sign, and what do we have? We have that Tc over T hot equal to delta Q cold over delta Q hot. Alright? Or I can rewrite this as delta Q cold divided by T cold will be equal to delta Q hot over T hot. So next, let me just rewrite the same equation. Okay, and let me just here just do a reminder about the sign convention for the heat. So heat going in is positive, heat going out is negative. So what does that mean? That actually this heat over here, this one is negative. So this at the end will give us what? Delta Q hot TH plus delta Q cold T cold will be equal to 0. So this will be what happens for the first cycle. Basically, the first cycle will be this one over here. Now let's see what happens for the second cycle, the one that will be with the prime. So basically, we have exactly the same thing. So second cycle, since all the Carnot cycles are operating between the same temperature reservoir, they all have the same efficiency according to the Carnot principle, the second Carnot principle. So over here we can have again that efficiency will be equal to 1 minus T cold over T hot equal to 1 minus delta Q prime cold over delta Q prime hot. So exactly as before, we're going to have T cold over T hot equal to delta Q prime cold over delta Q prime hot. We can rewrite this as delta Q prime cold Tc equal to delta Q prime hot T hot. And for the same reason as over here, since the heat going out is negative, this one here will be negative, and we can rewrite that delta Q prime hot over T hot plus delta Q prime cold over T cold is equal to 0. Okay, so from here, I think it's clear that we can keep doing this for all the cycles. Okay, so all the cycles, and at the end, adding up all cycles, what do we have? So we're going to have, let's say, The first one will be what? Delta QH over TH plus delta Q cold over T cold plus delta Q prime hot T hot plus delta Q prime cold T cold plus all the other ones, and they should all be equal to 0. Okay? So in a more mathematical form, we can just rewrite this as follows. So if you remember from the integration, when you add all the different ones, all these different cycles, basically what you're doing is to integrate. So you can replace the summation sign by the integration sign, and here we go around a surface. So sometimes in mathematics you can put this, and now we're just going to simplify this by the expression summation of all the delta Q over T, and if the system is reversible, as was our assumption over here, this is for a reversible cycle, a Carnot cycle, all these ones should be equal to 0. And this is actually the first part of the Clausius theorem. So basically, Clausius theorem says that Clausius theorem for a reversible cycle means what? If the system is reversible, once you adopt all the ratios of delta Q over T, they should all be equal to 0. Okay? Okay, so we know that we were able to define a reversible cycle, but what is the opposite would be a non-reversible, or what is called an irreversible cycle. So if you remember from Carnot first principle, basically we had that the efficiency of an irreversible cycle or non-reversible is always lower than the efficiency of a reversible cycle. So basically for an irreversible cycle, the efficiency is what? 1 minus Q cold over Q hot. And for a reversible cycle, we can replace the Q's by what? The temperatures. So we have this. Okay, now since the temperature and the heat are absolute values, in mathematics what we can do is the following. So again, we can eliminate the 1, but now since we have minus on each side, this means that the equality sign needs to be reversed. Okay, so basically by doing so, we can just rewrite that Q cold over T cold on one side. Let's say we put on this side Q hot over T hot. So if the sign needs to be this way, now we need to reverse it. So it will be this way. Okay? And now, same thing as before. If you remember the sign convention for Q, let's see what color did I use before. The orange, so the Q going in is positive, the Q going out is negative. So that means we have a minus sign. And now, what we're going to have from here that we can say that Q hot over T hot. So this will be here for the reversible. And this side will be here for the irreversible. So we have that Q hot over TH reversible. Plus we move everything to this side. So plus Q cold over T cold irreversible. And again, since we have the minus sign, this is going to switch again. Lower than 0. So if we integrate, what do we have? Let's integrate one by one. So we're going to have QH TH reversible plus Q cold T cold irreversible. Maybe I should do here the integral as well. So we have this, should be lower than 0. But if the system is reversible, we just saw that this over here should be equal to 0. So that means at the end that we have that the interval for Q cold T cold must be equal to 0 for an irreversible cycle. Or if I just change slightly the notation here to make it the same as before, it means that change in heat over the temperature for an irreversible cycle needs to be lower than 0. So this will be the Clausius theorem for an irreversible cycle. Alright, so let me just summarize this very quick. So basically at the end, Clausius just saying that the ratio delta Q over T is equal to 0 if the system is reversible and it is negative or lower than 0 if it is non-reversible or irreversible. Okay. Alright, I will stop this video here, not to make it too long, but make sure that just after this video you go to the next one. Okay, thank you so much for your attention.